Thank you. Good morning, dear participants of the conference. I would like to present to your attention my report, Spatial spectroscopy of magnetron discharge argon plasma using a radiative-collisional model.
Назад, вниз надо листать.
Okay. Thank you. Magnetron discharge in crossed electric and magnetic fields can be realized for various combinations of cathode material and plasma forming gas, and creates streams of high energy ions that bombard the target cathode. This slide shows the typical design of magnetron sputtering system with electromagnets and the characteristic discharge parameters implemented in this research work. The diagnostic of magnetron plasma has a number of features determined by the physics of the discharge. The plasma contains atoms and ions of the plasma-forming gas and the material of the target cathode, as well as various groups of electrons, such as knocked out from the surface due to the secondary emission, participating in a close drift in the magnetized region of the discharge, accelerating in an electric field in the ionization region, and some electrons of a glow charge. These electrons play different roles in the formation of the distribution of populations over the energy levels of this inert gas. In addition, there is a substantially irregular distribution of these groups of electrons in space, which requires the use of various diagnostic methods. At the Bauman Moscow State Technical University, we have a complex for diagnostics of magnetron discharge plasma. It was created on the base of Avantis RSpec 2048 spectrometer. Its configuration designed for the visible and near infrared spectral ranges. The method of spectral diagnostics is based on the registration of spectra from different areas of the discharge of the magnetron with electromagnets using a specially developed true coordinate optical collimator positioning system with a system of diaphragms and collimating lenses based on drives with stepper motors, which is shown on this slide. It allows to move the optical collimator here with a predetermined step up to 0.2 millimeters, both along and across the axis of the discharge. After passing through the system of diaphragms, the radiation of the magnetron plasma in the vacuum chamber is focused by a collimation lens at the end of the fiber optic cable. The axis of the optical collimator is perpendicular to the axis of discharge, which makes it possible to exclude intense dusting of the elements of optical system. Computer automation of the spectral complex allows, in addition to recording emission spectrum, to fix the spatial distribution of the radiation intensity of a specific spectral line when the optical collimator is moved across the discharge axis. The method of determining magnetron plasma parameters such as electron temperature and density presented in this report is based on minimization of difference between relative intensities of argon spectral lines in near-infrared obtained by optical emission spectroscopy experiment at various discharge areas and calculated theoretically by some model. In the optically thin plasma approximation, intensity of some optical transition from upper energy I to the lower J can be evaluated by means of this expression. For having calculated excited states, population densities, and I, we use a collisional radiative model, very similar to those that were used in these papers, but our model is slightly simplified. This model describes kinetics of ground state, yes, and first 40 excited states of argon atom. All considered states are presented in this table in Paschen notation with excitation energy and statical weight. In order to obtain all energy levels populations, it is necessary to solve a set of balance equations. They include the following processes: electron impact excitation and de-excitation, electron impact ionization from ground state or maybe from some excited states, and of course spontaneous light emission. Electron impact excitation rate depends on this coefficient. In this expression, E is delta E is excitation energy, Q is electron impact excitation cross section, V is electron velocity, and F is an electron energy distribution function, which is assumed to be Maxwellian in this work, but there are some variants of using non-Maxwellian functions. This will make the model more complex, but could increase the accuracy of results obtained. Electron impact cross-section for argon excitation from ground state were retrieved from plasma data exchange project, and here you can see some of them. Cross sections for excitation from one metastable state to another were retrieved from this article. De-excitation coefficients here were calculated in accordance with the detailed balancing principle. Electron impact ionization is another significant process in the collision radiative model. Its rate coefficient is quite similar to that for excitation, but the difference is in ionization energy from specific energy level. The required ionization cross sections were retrieved from this paper. The considered set of balance equations has two independent variable factors, the electron density and electron temperature. For each pair of ME and TE values, we obtain as a solution an array of populations of all considered 40 levels of the argon atom. After that, we can theoretically calculate intensity for any spectral line we are interested in. The meaning of the technique is to obtain the theoretical values of the intensities for a set of spectral lines. of argon by varying the values of the independent variable factors N, E, and TE, and to compare them with their intensities obtained experimentally in different regions of the discharge by means of spatial optical emission spectroscopy. Before comparison, each of the intensities obtained by both methods should be normalized to the sum of the intensities of all the lines under consideration. The search for the closest to the real pair of electron density and temperature is performed by minimizing this merit function. Here we can see an example of results obtained for one position of the optical collimator. It was 30 millimeters from discharge axis, and the distance to the cathode plane was 5 millimeters. Here is example of experimentally obtained intensity distribution along the cathode plane for one spectral line from this set. It was 763.5 nanometers. This slide presents obtained results for several points, distances from the discharge axis along the cathode plane with constant 5 millimeter distance from it. We can see a slight correlation between the obtained electron density and the light emission intensity spatial distributions. Here is some increase in the region with the highest magnetization. As for electron temperature results, unfortunately there is no any visible correlation, but the obtained values of temperature that are 3 to 5 electron volts are quite comparable to some literature data. And let's move on to conclusions. Spatial optical emission spectroscopy method combined with collisional radiative theoretical model can be the basis of plasma parameters, spatial distribution determination technique in magnetron discharge with highly irregular structure. First results obtained by this technique show slight correlation between electron density and emission intensity distribution. Electron temperature values of about 3 to 5 electron volts obtained in different charge regions are quite comparable to literature data. Further development of this work involves the following steps. Improvement and complication of the collision radiative model, taking into consideration light self-absorption and radiation decay, and trying maybe a non-Maxwellian electron energy distribution function variant. Calculations, comparisons, and determination of discharge plasma parameters in a larger number of spatial positions and sections with a smaller spatial step, and estimation of the determined results accuracy and maybe comparison with values obtained with other diagnostic techniques, for example, probe diagnostics. Thank you for your attention. I will be happy to try to answer your questions. Thank you.